Okay, then let's start chapter 8 of class 11 physics, that is mechanical properties of solids. Let's begin. The main topics here are stress and strain, Hooke's law, stress strain curve, elastic modulus, applications of elastic behavior of materials. These are the main topics here. Now let's start with introduction here. In chapter 6, we studied the rotation of bodies and then realized that the motion of a body depends on how mass is distributed within the body. Okay, the motion of a body depends on how mass is distributed within the body. We restricted ourselves to simpler situations and rigid bodies. A rigid body generally means a hard solid object having a definite shape and size. But in reality, bodies can be stretched, compressed, and even bent. Even the appreciably rigid steel bar can be deformed when a sufficiently large external force is applied. The first point to understand here is that motion of a body depends on how mass is distributed within the body. And rigid bodies in reality do not exist. And normally any kind of real rigid body, considering an even an iron bar, if we apply sufficient amount of external force, it can also bend and deform. An ideal rigid body is a body which is having a definite shape and size, but that is very hard to see by in reality. This means that solid bodies are not perfectly rigid. Any kind of solid body, most of the solid bodies are not perfectly rigid. A solid has definite shape and size, a property of matters, states of matter that is solid. It has a definite shape and size. In order to change or deform the shape or size of a body, a force is required. Okay, if you stretch a helical spring by gently pulling its ends, the length of the spring increases slightly. Okay, when you leave the ends of the spring, it regains its original shape and size. The property of a body, by virtue of which it tends to regain its original shape and size when applied force is removed, is known as elasticity. Okay, let's read that again. The property of a body, by virtue of which it tends to regain its original size and shape when applied force is removed, is known as elasticity. The property of a body through which it can regain its original shape, it can come back to its original shape after the applied external force is removed. It will change its shape once an applied external force is applied, but when this external force is removed, it will come back to its original shape. That this specific property of a few solids is known as elasticity, and the deformation caused is known as elastic deformation. The deformation, the change in shape and size we see, is known as elastic deformation. However, if you apply force to a lump of putty or mud, they have no gross tendency to regain their previous shape. They get permanently deformed. Not all objects have the property of elasticity. For example, if you take mud or sand or whatever it might be, and you apply force to this mud, it will get deformed, but there is no reformation. It won't come back to its original shape. That is why it is a non-elastic material. It cannot get reformed. Such substances are called as the when objects or substances when applied with external force are deformed but do not return to their original shape and size and get permanently deformed are called as plastic substances. This is a property, not the actual matter itself. Just like elastic, plastic is also a kind of property, plasticity. And this property is not called as plasticity. Elasticity, when the external force is removed, the reformation of the body is seen, the body comes back to its original shape and size, is known as elasticity. Where opposite of that, if the applied force is removed but the object does not return to its original shape and size and does not reform, is known as plasticity. The property is known as plasticity. The materials are called as plastic materials. And before, elastic materials, property elasticity. Putty and mud are close to ideal plastics. There is not only ideal elastic objects, there are also ideal plastic objects, where these put and muddy, which almost which contain which remain deformed the most ideally, so they are called as ideal plastics. The elastic behavior of materials plays an important role in the engineering design. It's true. For example, while designing a building, knowledge of elastic properties of materials like steel, concrete, etc. is essential. Otherwise, the building will collapse. If proper idea of the materials is not known and not planned, the building will most probably collapse, endangering many lives. So it must be thoroughly investigated depending on the plane the building is being constructed, the materials required, the body of the building, etc. The same is true in design of bridges, automobiles, ropeways, etc. One could also ask, can we design an aeroplane which is very light but also sufficiently strong? Can we design an artificial limb which is lighter but stronger? Why does a railway track have a particular shape like eye? Why is glass brittle while brass is not? These are all things which will answer us. Answers to such questions begin with a study of how relatively simple kinds of loads or forces to act to deform different solid objects. We understand all answers to those questions by understanding how forces and loads uh, act on objects, deforming them. In this chapter, we shall study the elastic behavior and mechanical properties of solids, which would answer many such questions. That's with the introduction. Now let's go to the next. No, the first main topic, that is stress and strain. When forces are applied on a body in such a manner that the body is still in the state of still in static equilibrium, it is deformed to a small or large extent depending upon the nature of the material of the body and the magnitude of the deforming force. Let's see that again. When forces are applied in a body such a manner that a body is still in static equilibrium, it is deformed to a small or large extent depending on the nature of the material of the body and the magnitude of the deforming force. What they are saying is, when we crush basically, if there is a box like this and we apply a force in this direction and in this direction, the net force on this body is zero. Net force which is equals to zero, because they are in opposite direction and equal in magnitude. But and that also means the body is in static equilibrium. But because of this force, this force is known as deforming force. deforming force. Because of this force, the body will get deformed. Even though the body is in static equilibrium, because of the deforming force, this body will get crushed like this. And this deformation depends on one, magnitude of deforming force, or basically the force, to the nature of the body. Nature of the body. Why it depends on the nature of the body is because naturally when we compare sand or mud to steel, obviously the sand, which is very plastic, will obviously get compressed more easily compared to a steel bar or something like that. Because of that, the deformation of this object depends on the nature of the body as well as magnitude of the deforming force. That is what they said here. Let's go back. Okay, then. Okay. Stress and strain when forces applied on a body in in such a manner that the body is in static equilibrium, it is deformed to a small or a large extent depending on the nature of the body and the magnitude of the deforming force. The deformation may not be noticeable visually in many materials, but it is still there when you compress, when you push against the wall, or when you push or try to bend a rigid iron steel rod. Although there is no visual deformation of the object, when you push a wall, you obviously don't see the wall going in or caving in. But even though it is not visual to us, there is still a minute deformation which will get restored. This is the elasticity of the wall or the metal rod basically. But it is there, like the with deformation may not be noticeable visually in many materials, but it is still there. When a body is subjected to a deforming force, a restoring force is developed in the body. This is also reason why, like when you push against a wall, when the normal force basically, if there is no force against us, when you push against a wall, we will obviously fall into the wall if there is no force against us. But we need to assume, because we are not falling into the wall, we need to assume there is another force acting on us, that is a normal force, and there is also the restoring force uh, that will be against the deforming force. When a body is subjected to a deforming force, a restoring force is developed in the body. This restoring force is equal in magnitude but opposite in the direction of the applied force. I have a doubt. Is this restoring force the is simultaneous with the opposite force, external force? Does this happen in the same time as the opposing force? Basically, I have a doubt if it is an action reaction pair, Newton's third law. It seems it is not a simple reaction force of Newton's third law. A reaction force in Newton's third law is always equal and opposite to an external applied force, and it acts on a different body. You push a wall, the wall pushes you back. A restoring force is internal force developed inside a deformed body due to its tendency to return to equilibrium. What actually happens when you apply force on a body? Suppose you pull a string, your hand applies an external force F, and the spring stretches due to that force, and due to intermolecular forces, it develops a restoring force. These are not Newton's third action reaction pair because the forces act on the spring on the same body. Okay. It only happens at the time when there is equilibrium, like when there is no moving, when it's not at the time when you are pulling a string, the force, like if the reaction force is equal to the applied force, wouldn't the if there will be no net force on the spring, so the spring should not stretch, but that is not happening. Clearly, when we apply force, the spring is stretching. What that means is the restoring force is not quite equal to the applied force. But here they clearly mention that the restoring force is equal and opposite in equal in magnitude, but opposite in direction to the applied force. So why the spring is still stretching is because they considered it in a equilibrium position. Okay, you are stretching a spring. After you have stretched, at some point, let's assume you stop and you hold it. At that time, the you still experience a pulling force from the spring. This is the restoring force. It is at the time of equilibrium that this applied restoring force is equal and opposite in direction to the applied force. That is one of the main reasons we feel when we stretch a string, for holding it in that position, we need to apply a force continuously. Okay, that is because of the restoring force. Okay, this restoring force is equal in magnitude but opposite in direction to the applied force. The restoring force per unit area is known as stress. Okay, there's a very important point. The restoring force per unit area is known as stress. Let's write that once. Mechanical properties of matter. Stress, restoring force per unit area is called stress. What is restoring force? Restoring force, the force developed due to intermolecular interactions to restore a deformed body. This restoring force is equal in magnitude and opposite direction of applied force. Okay, let's go back. And the formula for stress, I'll write that too. Stress, which is equals to force by area, restoring force per unit area. Okay, then if F is the force applied normal to the cross section on area of cross section of the body, this is the force applied. We know that the stress is restoring force per unit area, but we are considering the force applied because we know that at equilibrium condition the applied force is equal to the restoring force. So at equilibrium position, stress is applied force per unit area, and this is if the force is applied normal to the cross section of the area, perpendicular to the cross section, and A is the area of the cross section of the area, I mean, or cross section of the body. Magnitude of stress is force by area. The SI unit of stress is Newton per meter square or Pascal, and in its dimensional formula is ml power minus 1 t power minus 2. There are three ways in which a solid may change its dimension when an external force acts on it. Okay, they're saying that there are three ways in which a solid changes its dimensions when external force acts on it. These are shown in figure 8.1. Let's see. Figure 8.1. First figure, a cylindrical body under tensile stress elongates by delta L. Okay, basically this is a cylinder and we are stretching it like this by applying force in the direction of the arrow mark, and if the initial length is L, the length has increased by L plus delta L. Then the second one, this is longitudinal tensile stress. This elongating here, and second diagram shows us shearing stress on a cylinder, deforming it by an angle theta. Basically, this is a cylinder, and instead of putting force here, the shearing stress is when you apply force in this direction and this direction. We are trying to deform it, bend it, and this can be understood by the initial angle of deformation here, and this is represented by delta x. Now C, we see a body subjected to shearing stress again here. When we push the book, this is very commonly observed here. When there is a book on a table and you keep your hand and drag it forward with the book, like this here, like this hand is pushing the book forward, but the base layer of the book is attached to the table. It's not completely attached, but due to friction, there's friction between the table and the book. Because of that, there is a, and we already know that friction is an opposing force, so it will be in this direction. Our force will be in this direction, and the book will deform like this. It must have been experienced by many people. It's very common. There's also tension in the book, that the book might tear, and this is the angle theta. And next is D, a solid body under a stress normal to the surface at every point, hydraulic stress. The volumetric strain is delta V by V, but there is no change in shape. Okay. This is when there is an object, the solid object, it is under stress in every direction. The stress is normal to the body in every point. Normally, this kind of stress is this kind of force, this restore the force, the applied force will be in this, like in normal to every point of the body. In cases such as when the body is inside water, hydraulic stress, where water will push on the body from all sides, even in the atmosphere where the air molecules will apply pressure on the body or apply force on the body in all possible directions. If there is a change, we can represent it. If there is a change, since it is in all possible directions, the only change we can observe here is volume, the change in volume, as it will most likely decrease. But if it will decrease, but normally it does not decrease, because when you put, if it is a very rigid substance, it will not decrease. That is what they're saying. There's no change in shape normally here. In figure 8.1a, a cylinder is stretched out. The first case here, elongation here, stretched out by two equal forces applied normal to its cross-section area. The restoring force per unit area in this case is called as tensile stress when it is longitudinal stress. When we are pulling on something and elongating its length longitudinal, then we call it as tensile stress. If the cylinder is compressed under the action of applied forces, the restoring force per unit area is known as compressive stress. And uh, instead of force in this direction, what if the force was in this direction instead? If the force was in that direction, then obviously the cylinder will get compressed. It will become something like this. It will become smaller. This stress is called as compressive stress. Tensile or compressive stress can also be termed as longitudinal stress, because it is elongating the object. Longitudinal, it's increasing the length or decreasing the length. Tensile strength, when we increase or elongate the body. Compressive stress, where we decrease the size of this cylinder. And longitudinal stress, and both of them, that is both of them. In the both cases, there is a change in the length of the cylinder. The change in the length of the cylinder, that is delta L to the original length of the body cylinder in this case, is known as longitudinal strain. Okay, basically, let's write down the cases. First, longitudinal stress involving length of the body, force along force normal to the area of cross section. Here we can see an example of that's not a very nice cylinder. Let's start again. Let's assume this is a cylinder, and when we elongate it, where this is length and this is delta L, or we compress it, where this is L, this is delta L, this is tensile stress and compressive stress. Compressive stress and tensile stress. Now shear stress, when this cylinder deforms like this, where this is the angle of deformation, and like this, shear stress, and basically hydraulic stress. Where the volume may decrease. And coming to strain, longitudinal strain, longitudinal strain basically is the elongation of the body slash compression, elongation slash compression of the body per actual length of the body is longitudinal strain. which is equals to delta L by L. Let's go back to NCERT. Longitudinal strain delta L by L. However, if two equal and opposite deforming forces are applied parallel to the cross section area of the cylinder as shown in figure 8.1b, here the forces are applied not normal to the area of the cylinder but parallel to the area of the cylinder or surface of the cylinder. If the two equal and opposite deforming forces are applied parallel to the cross-sectional area of the cylinder, then there is a relative displacement in between the opposite faces of the cylinder. The restoring force per unit area developed due to the applied tangential force is known as tangential or shearing stress. Here, I did not mention it here, but let's mention it now. This is delta x force parallel to the surfaces delta x displacement between faces or deformation or distance between faces or deformed faces, distance between deformed faces, that is surfaces. That is called as shearing or tangential stress. Okay, then a result of applied tangential stress, therefore, is a relative displacement delta x between opposite faces of the cylinder, as shown in figure 8.1b. The strain so produced is known as shearing strain and is the ratio of relative displacement of faces delta x to the length of the cylinder. And why we say it is equal to tan theta is because this length, which is tan theta, which is equals to perpendicular by hypotenuse, and if we consider this an 90-degree angle, tan theta, which is equals to delta x by L, and this is obviously shearing strain or tangential strain. Shearing strain, let's see that again. Result of applied tangential force, there's a relative displacement between delta x between opposite faces of the cylinder at the strain so produced is known as shearing strain. It is defined as a ratio of displacement of the faces delta x to the length of the cylinder. Shearing strain, which is equals to delta x by L, which is equals to tan theta, where theta is the angular displacement of the cylinder from vertical original position of the cylinder. Usually theta angle of deformation is very small, and tan theta is nearly equal to theta if theta equals 10 degrees. For example, there is only 1% difference between theta and, okay, basically they are saying that when theta is very small, tan theta will approximately be equal to theta when theta is very small. So if there is a 10 degree, if there is a 10 degree, like the angle of deformation or angle of displacement is 10 degrees, then we consider that the shearing strain is also 10. There is, if you have noticed already, there is no unit for strain because it is length by length, and in that case then the meter will get cancelled and strain will be unitless. It can also be visualized when a book is pressed with the hand and pulled horizontally, as shown in figure 8.2c. Thus, shearing strain is equals to tan theta, which is approximately equal to theta in figure 8.1d. A solid sphere placed, the next figure here, a solid sphere placed in fluid under high pressure is compressed uniformly on all sides. The force applied by the fluids act in perpendicular direction at each point of the surface, and the body is said to be under hydraulic compression. This leads to decrease in volume without any change of its geometrical shape. Why there is no change in its geometrical shape is because the force is equal and normal in every point of the surface of the body. The body develops internal restoring forces that are equal and opposite to the forces applied by the fluid. The body restores its original shape and size when taken out of the fluid. The internal restoring force per unit area in this case is known as hydraulic stress. And in the magnitude, it is equal to the hydraulic pressure applied pressure per unit area. The stress strain obtained by a hydraulic pressure is called as a volume strain and is defined as a ratio of change in volume of the object to the original volume of the object. Volume strain delta V by V. Since the strain is a ratio of change in dimension to the original dimension, it has no units or dimensions or dimensional formula. That is what I said. Let's go to the next main topic, which seems to be very small here, only being 2 paragraphs, 2 to 3 paragraphs, but not very small indeed. Hooke's law. Stress and strain take different forms in the situations depicted in 8.1 figure. For small deformation, the stress and strain are proportional to each other. This is known as Hooke's law. Okay, what Hooke's law is saying is that stress, which is force per unit area, and strain, change in dimension to the original dimension, take different forms like longitudinal, compressive, tensile, etc., or shear or volume, different forms in the situations, in many different situations. For small deformation, the Hooke's law starts, where for small deformations, for minute deformations, the stress and strain are proportional to each other. This is known as Hooke's law. Basically, he's saying that the law is saying that for small deformations, stress is directly proportional to strain, where stress, which is equals to K times strain, where K is the proportionality constant and is known as the modulus of elasticity. Hooke's law is an empirical law and is found to be valid for most material. However, there are some materials which do not exhibit this linear relationship. Okay, what this stress is directly proportional to strain means is that we know that stress is the restoring force per unit area and strain is the deformation or the change, like the change in dimension per actual dimension. So knowing that, how can we understand stress is directly proportional to strain? What this means, stress is directly proportional to strain, is that stress is not constant. When we elongate a spring for 2 centimeters and 6 centimeters, the restoring force developed in the spring is different at 2 centimeter position and 6 centimeter position. That means stress, according to stress, is directly proportional to strain. For Hooke's law, for some substances, as the elongation, the strain, which is the change in dimension, as this keeps on increasing, as the dimension change increases, higher the elongation. For example, in case of tensile stress, higher the elongation, higher the restoring force. This stress will also increase proportional with strain till a certain point. That is what they mean, stress is directly proportional to strain. The restoring force will continue to increase as increase in elongation till a certain point, and K represents the modulus of elasticity. Hooke's law is an empirical law and it is found to be valid for most materials. However, there are some materials which do not exhibit this linear relationship. Now let's see the stress strain curve here. The next main topic is stress strain curve. The relation between stress and strain for a given material under tensile stress can be found experimentally. Okay, we can find the, what they are saying here is, we can find the relation between stress, force per unit area, and strain, change in dimension per original dimension of a given material, any material it may be, under tensile stress, elongating stress, can be found, we can find it experimentally. In a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force. Okay, we stretch a cylinder or a wire by a standard force. The fractional change in length, that is the strain, and the applied force need to cause the strain are recorded. Okay, what we record here is, after doing the experiment, what we record is the small change in length, that is delta L, that is a strain, delta L by L strain is recorded, along with the force needed to cause the strain, that is basically stress. The force, applied force required to cause the change in the fractional change in the length of this wire or cylinder, both are recorded. Then at first step we keep minimum applied force, so according to Hooke's law the strain also will be minimum. Next, trial 1 is over. Now let's go to trial 2. Applied force is gradually increased in steps and the change in length is noted. As we keep on increasing the force in the second trial, third trial, we keep on increasing the applied force and note the strain. If it is increasing, if the length is increasing more or it's not increasing at all, we note that down. Then a graph is plotted between the stress, which is equal to the magnitude to applied force per unit area, and the strain produced. Now what we do is, we have all the values. Now just draw a graph. A typical graph, now we see an example graph. A typical graph for a metal is shown in figure 8.2. Analogous graphs for compression and shear stress may also be obtained. Similar graphs like here can also be obtained for shear stress, basically the deformation one, like when we push it parallel to the forces applied parallel to the surfaces, and we measure it tan theta, strain is tan theta, stress is force per unit area. We can also do it for shear stress. Now let's see the stress strain for tensile stress. The stress strain curves vary from material to material, depends on the material. These curves help us to understand how a given material deforms with increasing loads. Okay, as we increase loads is basically forces, we can understand how much the object deforms with given loads. The slope of this graph is basically the modulus of elasticity from Hooke's law. From the graph, we can see that in region between O and A. Let's observe the graph first. A typical stress strain curve of a metal. If we observe, this is a permanent set. This is a stress, this is a strain, and for the initial till point A, stress is directly proportional to strain, and suddenly at this point of stress, this is the proportional limit, and at this point the strain will drastically increase for a small increase in strain. The strain will drastically increase for a small increase in stress. This is represented here, and even at after this yield point, at yield point, the strain will drastically increase even more, even when the stress is not at all changed. Basically a straight line here. And after this point, this is known as the yield point at B, then this is not proportional anymore, and even with small increase in stress, the strain will rapidly increase until at some point, that is D, this the even when the applied force, that is stress, is decreasing, the strain will continue to increase, and at a certain point, that is called a fracture point, the object will basically break. Okay, basically till a certain point, that is a proportional limit, the stress is directly proportional to strain. As the strain increases, as the elongation increases, the stress, like the restoring forces, will also increase. But after the proportional limit, at yield point, that is at B, there is no proportionality now, and even with slight increase in the stress, that is applied force, the strain will rapidly increase. It will increase more. There will be more stretching of the object, and after this yield point, there will be even more increase in strain, even though the stress is maintained at a limit, and after point D, it will completely increase. The strain will increase even more when the force is decreased, and at E, the object will finally break, fracture. Okay, from the graph we can see that in the region O to A, this region till the proportional limit, the curve is linear, that is following the proportionality. In this region, Hooke's law is obeyed. The body regains its original dimensions and the applied force is removed. Till this point A, if we at that point, after stretching, after applying a stress equal to this point, at that point the body will, after removing that applied force, the body will regain its original dimensions. In this region, the solid behaves as an elastic body. This is also known as the elastic region, where the body will regain its original shape back after the applied force is removed. This is the elastic region of the graph, and it will regain its body. In the region A to B, if we observe after the proportional limit, A to B, stress and strain are not proportional, but the body still returns to its original dimension when the load is removed. Okay, here if we see at point A and B, this one, if we see at A and B, till O and A, it was completely proportional, completely obeyed Hooke's law, and it was completely elastic. Even though at A, B, at point from A to point B, it's still elastic. After we release it, it will come back to its original position. But it is not proportional anymore. Even though stress might increase little, the strain will increase much more than the stress. But till O to A, the forces, as stress increases little, strain also will increase little. But from A to B, when stress increases little, strain will increase more compared to the stress. But after, even at till point B, after we release the applied force, the body will come back to its original dimensions. It is still a bit elastic. The point B of the curve is known as the yield point, also known as the elastic limit. Point B is the yield point, also known as the elastic limit, and the corresponding stress is known as yield strength of the material. This stress that is marked here, sigma y at point B, this is the stress at point B. This stress is called as the yield yield stress, yield strength, or the point B is known as elastic limit or yield point. This distance, this from O to this point, let's assume it is some G, O to G. This O to G point is a permanent set which is less than 1% of the total length of the body. The strain till less than 1%, the strain will be directly proportional, but after it crosses a certain limit, it will cross the elastic limit and will not be able to come back to its original shape anymore. And after the yield point, that is the yield strength, after the yield point, after the yield strength, if the load, that is the stress, increases further, the stress developed exceeds the yield strength and strain increases rapidly, even for a small change in stress. That is what I said. The portion of the curve between B and D shows this. Like if we observe from point O to C or point O to B, we can observe that till this much stress, that is till point B, the change in dimension was only this much compared to increase in stress, which was this much. But after point B, that is the yield point or the elastic limit, we increase the stress only this much, but the increase in strain is phenomenal, being this large. That is what they're saying. The portion of the curve between B and D shows that small change and rapid increase of stress when the load is removed. That is, let's say that between okay, let's read first. When the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this case, even when stress is 0. Okay, let's assume there is a point C. B is the yield point and D is the fracture point or proportional limit. Basically, proportional limit is D point, where after this proportional limit D, there's no proportionality. As stress increases, as stress decreases, normally strain also should decrease. But even though the stress decreases, the strain continues to increase. So the proportionality limit is broken. It's no longer proportional at D and E. It's no longer proportional at D and E, where even though the stress decreases, the strain not decreasing but increases. Okay. As for before that, that is a point C between B and D, that is a yield strength point or the yield point or the elastic limit, and the proportional limit. Between these 2 points, at point C, let's assume after crossing the elastic limit at point C, we remove the stress, that is, we remove the applied force on the body. Let's assume we did that. But after we remove it, the body will not come back to its original point. The body will not come back to its original point. It will not come back to its original dimensions. This is known as crossing the elastic limit. The strain is not zero. The material is said to have a permanent set. Okay, this 1%, after it crosses the C, this will be permanent. It will not get restored anymore. It will not get restored anymore. Even when stress is zero, the strain is not zero, because even though we remove the applied force, the deformation, it will not go back. So the strain will remain, because strain is change in dimension to original dimension. There is a change in dimension induced, it will still stay there even though the applied force is removed. This is a permanent set. The deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength of the material. This point is the ultimate tensile strength of the basically this body. Till this point, the body will stay like it will, the stress will be directly proportional to strain. But after this point, even though the stress decreases, the strain will continue to increase. It will cross the proportionality. Now this is the point. The point A is the proportional limit, and proportionality is gone. Point B is the yield point or the elastic limit, and D is the ultimate tensile strength of the material. Ultimate tensile strength of the material, and E is the fracture point. Beyond this ultimate tensile strength, that is a point D, additional strain is produced even by a reduced applied force, and fracture point occurs at point E. With the ultimate strength and fracture points D and E are close, the material is said to be brittle. If they are far apart, the material is said to be ductile. What they're saying is the difference between brittle and ductile materials. Okay, let's assume the distance between point D and E is very much farther apart, very far. In such a case, D is the ultimate tensile strength of the object and E is the fracture point. So in such a case, when we continue to apply force after the ultimate tensile strength, the object will continue to elongate. This only happens when D is very far from the fracture point. This continue to increase until it reaches the fracture point. If the distance between D and E is far, the material is said to be ductile, meaning it can be elongated into long wires. It can be elongated into long wires. That is basically useful for us for many purposes. But let's assume the distance between D and E is less. In such a case, immediately after reaching the let's say the ultimate strength of the object, the ultimate tensile strength, the object will just break immediately after reaching the ultimate tensile strength, because the fracture point is very near. The material will immediately break. We can't stretch it into long wires. It will immediately break. Because of that, the materials are classified into brittle and ductile. When D and E are close, it is brittle. It immediately breaks after ultimate strength is reached, ultimate tensile strength is reached. But when it is ductile, the distance between the ultimate tensile strength and the fracture point is very far apart. This is the stress strain curve for elastic tissue of aorta, the large tube vessel carrying blood from the heart. This is basically this is the largest arteries stress strain curve. Aortas, it's an artery. Stress strain curve of elastic tissue of the aorta, the largest tube vessel carrying blood from the heart. Okay, this is stress and this is strain. We can identify that it is very elastic because till this many Newton meter square, that is this many pascals, it is still proportional, and as it is proportional, basically that's all. Just given for example, given as an example here. As stated earlier, the stress strain behavior varies from material to material. For example, rubber can be pulled to several times its original length and still returns to its original shape. Okay, normally when iron, if we consider, it has less than 1% strain stress where it is elastic. But rubber, if we take, if we stretch it many times its original length as well, it will come back to its original shape, which is completely different from iron, which only from 1% it will not come back to its original length. So it depends on the material. The above figure shows a stress strain curve of the elastic tissue of aorta present in the heart. Note that although elastic region is very hard, the material does not obey Hooke's law over most of the region. Secondly, there is no well-defined plastic region. Substances like tissue of aorta, rubber, etc., which can be stretched to cause large strains, are called as elastomers. Okay. If we observe this, the stress strain graph of aorta, we can see that it is very elastic indeed because it's increasing, but it's not reaching a non-proportional area. We cannot say it's proportional because if it is proportional, it should be something like this, but that is not the case here. It is something like this. That means even though for a large increase in stress, strain is not increasing very much. This should be the case for a heart tissue because if the strain is very much for minute stress, then the expansion cannot be sustained in our body. The space required would be very much. So obviously it should be like this. It is very elastic, and a rubber, which is which will show much strain for less stress, is also kind of elastic material. It does not follow Hooke's law or most of the region because like for even a small increase in stress, for a high increase in stress, there is not much increase in strain here. Only in this specific region it will show some proportionality anyways. And these kind of substances which can be stretched to cause large strains are called as elastomers. Important to remember. Let's see the elastic modulus as well. The next main topic, that is elastic modulus or elastic moduli. We saw that stress is directly proportional to strain, and stress which is equals to k times strain, and k, which there it was elastic modulus. Now let's see more details of this k proportional constant. The proportional region within the elastic limit of the stress strain curve that is region OA in figure 8.2 is a great importance for structural and manufacturing engineering designs. Here if we see in figure OA, figure 8.2, this proportional limit, that completely proportional region, it is of great importance for structural and manufacturing engineering designs. The ratio of stretch, stress and strain is called modulus of elasticity, is found to be a characteristic of a metal. Basically, stress, which is equal to k times of strain. So obviously, k, which is the modulus of elasticity, is equals to stress by strain. Stress by strain, which is equals to modulus of elasticity. Longitudinal stress by longitudinal strain is Young's modulus. But I will continue that after a 10 minutes break. Okay, then let's continue. Young's modulus. Experimental observations show that for a given material, the magnitude of strain produced is same whether stress is tensile or compressive. The ratio of tensile or compressive stress is the longitudinal strain is defined as Young's modulus and is denoted by a symbol Y. Okay, what they are saying is for any kind of given material, for any given material, the magnitude of strain produced is the same whether we do it as a tensile stress or a compressive stress. So, for any kind of longitudinal stress that may be tensile or compressive, the ratio of tensile or compressive stress to that of longitudinal strain is defined as Young's modulus, denoted by symbol Y. Y, which is equal to sigma by epsilon, where sigma by epsilon is basically longitudinal stress by longitudinal strain. From equations 8.1 and 8.2, we know longitudinal stress is basically force per unit area, and longitudinal strain is basically the change in dimension per actual dimension. We will get Y, which is equals to force times length by area times change in length. Since strain is a dimensionless quantity, the unit of Young's modulus is same as that of the stress, that is Newton per meter square or Pascal. Table 8 point gives the values of Young's modulus and yield strengths of some materials. From data given in table 8.1, it is noticed that for metals, Young's modulus are large. Okay, what we can understand what a Young's modulus is. What a Young's modulus is stress by strain. Basically, the force applied, the stress per the change deformation. So for metals which need high force to be applied for a small strain, obviously we can understand the Young's modulus would be obviously large. So Young's modulus is large for materials which require high strength, high stress to produce a minimal strain. And when Young's modulus is small, meaning that strain is comparatively larger than stress. In such a case, it means that the materials have higher elongation for smaller amount of stress. Material aluminium, Young's modulus is 70, the ultimate strength, tensile strength, where it immediately reaches the goes down, where stress, even with minimal stress, it will become more strain, that is 110 Newton per meter square into 10 power 6, 110 into 10 power 6 Newton per meter square. Here, this 70 into 10 power 9 Newton per meter square is the Young's modulus of aluminium, and yield strength is basically the point where proportionality is gone. These are substances tested under compression, with the highest being steel, having the highest Young's modulus, highest ultimate strength point, similar to copper, and having the highest yield strength, steel having the highest yield strength as well. Now let's see, therefore, these materials that are metals require large force to produce a small change in length. To increase the length of a thin steel wire of 0.1 centimeter per square cross-section area by 0.1%, a force of 2000 Newton is required. Ridiculous amount of force for a small amount of increase. Basically, to increase the length of a thin steel wire, the area is very small, 0.1 centimeter square cross-section area, by 0.1% only, a force of 2000 Newton is required. The force required to produce the same strain in aluminum, brass, and copper wires at the same cross-sectional area are 690, 900, and 1010, 1100 Newton respectively. It means that steel is more elastic than copper, brass, and aluminum. It is for this reason that steel is preferred in heavy-duty machines and in structural designs. Wood-borne concrete glass have rather small Young's modulus. Higher the Young's modulus, higher the elasticity of the material. Because higher the Young's modulus, higher the slope of the, higher the proportionality and higher the elastic limit. That is yield point. If we see the highest yield point, that is, it is for steel. Steel has the highest ultimate strength of 400 and yield point of 250 into 10 power 6 Newton per meter square. Is a very large value. Let's see the example here. A structural steel rod has a radius of 10 mm and a length of 1 meter. 100 kilonewtons force stretches it along its length. Calculate stress, elongation, strain on the rod. Young's modulus of the structural steel is 2 into 10 power 11 Newton per meter square. What they gave is a radius of the steel rod, which is 10 mm, with which we can calculate the area. The force, the force applied, which is 100 kilonewton. We already got the force. We need to find stress, which is force per area, elongation, which is change in length per unit length, which we can find through Young's modulus using the Hooke's law formula. Okay, stress, which is equals to F by R. So let's say we assume that the rod is held by a clamp at one end, the force is applied at the other end parallel to the length of the rod. Then the stress on the rod is given by F by A is equals to F by pi R square, which if we substitute the values, we will get it as 3.18 into 10 power 8 Newton per meter square. The elongation is equals to delta L, which is equals to F by A times L by Y. If we substitute the values, we will get as 1.59 into 10 power minus 3 meter, that is 1.59 millimeter, which is very less for even 100 kilonewton strain, force. The strain is given by delta L by L, which is seen in percentages here, where we took 1.59 to be approximately 1.6 and wrote it as 0.16 percentage. Let's see the next question. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3 mm, are connected end to end. When stretched by a load, the net elongation is found to be 0.7 mm. Obtain the load applied. Since they are connected together, the load applied, the force applied should be equal for both of them. And using the Young's modulus, we can indeed find the values here. Basically, we know the length of the both of the rods, and we also know the diameter with which we can find area, and we know one of the rods elongation through which we can apply the force. Like from the steel rods, okay, the net elongation is found to be 0.7 mm, not for one rod's elongation. Then it's going to be a little more complicated. Let's see. The copper and steel wires are under a tensile stress because they have same tension. The force on them is same and same area of cross section A. From 8.7 we have a stress which is equals to strain into Young's modulus. Therefore, W by A, that is force by area, which is equals to Young's modulus into delta LE by delta LC by no matter no matter the strength and strain. I mean, we know that stress is same for both of them. This is obviously because the area is same, the force is also same. Thus, the stress experienced in both of the rods will be same. So these both we can equate. That is Young's modulus of copper into elongation of LC. That is change in length of copper rod by strain, basically strain formula. C and S refer to copper and stainless steel respectively, or basically we get delta LC by delta LS, which is equals to YS by YC into LC by LS. And we already know the values of Young's modulus, which is not given, but from our table we can find out the values of Young's modulus of steel and copper, and the lengths of the rods are already given, and the ratio of the change in length of copper by change in length of steel, we will get it to be around 2.5. And we know that the total elongation is 7 into 10 power minus 4 meter, or 0.7 millimeter. And solving these above equations, we will get that we can take LC, delta LC, which is equals to 2.5 into delta LS, and substitute this in this equation. We will get delta LC, the change in length of copper, will be 5 into 10 power minus 4, or 0.5 millimeter, and steel obviously being 0.2 into 10 power minus 4 millimeter. From this we can observe and conclude that the elongation of steel is much less compared to elongation of copper for a same stress and same area applied, same stress applied. That is because steel has a higher Young's modulus. Okay, let's go to the next question. Example 8.3. In a human pyramid in a circus, the entire weight of the group is supported by legs of a performer who is lying on his back. Is shown in this figure. Entire weight of the group is supported by this guy here with his legs stretched out like this. Just in case, let's read it again. In a human pyramid in a circus, the entire weight of the balanced group is supported by the legs of a performer who is lying on his back. The combined mass of all the persons performing the act and the tables, plates, etc. involved is 280 kg. The mass of the performer lying on his back at the bottom of the pyramid is 60 kg. Each thigh bone, that is femur, of this performer has a length of 50 centimeter, half a meter, and an effective radius of 2 centimeter. Determine the amount by which each thigh bone gets compressed under the extra load. Okay, let's see the answer. Total mass of all the performers of tables, plates, etc. is 280 kg, and mass of the performer is 60 kg. The mass supported by the legs of the performer at the bottom of the pyramid, which is equals to 280 minus 60. That is 220 kg. Weight of the supported mass, which is equals to 2000 Newton, 2156 Newton. weight supported by each thigh bone, if we divide it by half, is 1000 Newton. And from table, we can calculate the Young's modulus for a bone, which is 9.4 into 10 power 9 Newton per meter square. Length and area, radius is given, through which we can find area, and we can find a cross section area, which is found out here, using which we directly get we already know the formula of the Young's modulus, through which we can find delta L, which is approximately 0.000091, or basically that much of a meter, or 0.0091 meter, I mean percent. Now let's go to the next subtopic under the elastic modulus, shear modulus. The ratio of shearing stress to the corresponding shearing strain is called the shear modulus of the material. This is represented by G. It is also called the modulus of rigidity. That one was called Young's modulus. And G, which is equals to shearing stress by shearing strain. Same formula, but just different terms. Or we already know that delta x by L, which we can equate it to tan theta, and for small thetas, tan theta, which is essentially equal to theta. As such, F by A times theta, the shearing stress sigma S can be expressed as sigma S, which is equals to G times theta. Basically, when we send F by A is shearing stress, when we send theta that side, it will become shearing stress, which is equal to G times theta, where G is the rigidity modulus or the shear modulus. SI unit of the shear modulus is same as the Young's modulus, which is Newton per meter square or Pascal. The shear modulus of a few common materials are given in table 9.2. It can be seen that shear modulus or modulus of rigidity is generally less than Young's modulus for most materials. G is essentially equal to y by 3. It is comparatively less than the Young's modulus. It is essentially related to the intermolecular bonding or intermolecular interactions, which controls the shear modulus. It's important to remember that shear modulus, which is approximately equal to y by 3, Young's modulus by 3. Here again, nickel having the tungsten having the highest shear modulus of 150, followed by nickel, followed by steel. After tungsten, it's steel, then comes nickel. After that, iron. The difference between iron and steel is massive, and so is that of steel and tungsten. Let's see an example. And this is in terms of 10 power 9 Newton per meter square or gigapascals. Very, very large. Where we can represent tungsten in terms of terapascals, which is 0.15 terapascals. Let's see the example here. A square lead slab of side 50 centimeters and thickness 10 centimeters is subjected to a shearing force that is on its narrow face, meaning it's parallel to the narrow face, of 9 into 10 power 4 Newton. The lower edge is riveted to meaning it's fixed to the floor. How much will the upper force edge be displaced? Let's read that again. There is a square lead slab. It's a square lead slab, meaning its sides are equal but not breadth. Its thickness is different. Its side, one side is 50 centimeter, other side is also 50 centimeter, and its thickness is 10 centimeter. It is subjected to a shearing force that is parallel to the surface, that is of magnitude 10 power 4. We need to calculate force per area per delta x by L, which is theta. We know G value from the above table. Lead, which is 5.6, which is very less compared to other materials here, which with lead having the least shearing modulus, but still in gigapascals. Now we have all the values we need. The lead slab is fixed and the force is applied parallel to the narrow face as shown in the figure. Area we can already find out since it's given as a square slab. Area which is 0.05 meters square. Stress strain applied is 9.4 into 10 power 4 Newton by 0.05 meter square, which will essentially become 1.8 into 10 power 6 Newton per meter square. That is the stress. We know that shearing strain, which is equals to delta x by L, is equals to stress. We know the thickness, which is basically 10 centimeter. Or wait, there's a narrow edge, so L will essentially be 50 centimeters itself. We know that shearing strain is equals to delta x by L, stress which is equals to, which is equals to stress by G. Therefore, the displacement delta x, which is equals to stress into length into G, 1.8 into 10 power 6 Newton meter square into 0.5 meter by 5.6 into 10 power 9 Newton meter square. We will essentially get delta x, which is equals to 0.16 mm. Okay, now let's go to bulk modulus. This is when a body is like hydraulic stress, is under hydraulic stress or some pressure, something like that. In section 8.3, we have seen that when a body is submerged in a fluid, it undergoes a hydraulic stress equal in magnitude to the hydraulic pressure. This leads to decrease in the volume of the body, thus producing a strain called as volume strain. The ratio of hydraulic stress to the corresponding hydraulic strain is called as bulk modulus. It is denoted by a symbol B, which is equals to minus P by delta V by delta V by delta normal. Okay. Basically, if it's same as Young modulus and bulk modulus. It is stress by strain, but here this is hydraulic stress by hydraulic strain. Hydraulic strain is change in volume per unit, not per actual volume, and P indicates the stress, that is hydraulic stress, which is indicated in negative because most of the cases the body will get compressed, meaning there will be an decrease in the area. To keep the bulk modulus positive, we keep a negative sign there. The negative sign indicates that with increase in pressure, a decrease in volume occurs, that if P is positive, delta V is negative. Thus, for a system in equilibrium, the value of bulk modulus will always remain positive. To keep the bulk modulus always positive, we keep the negative sign there. SI unit of bulk modulus is the same as that of Young's modulus as well as rigidity modulus or shear modulus. It is Newton meter square. Newton per meter square or Pascal. The bulk modulus of few common materials are given in the right table here. The reciprocal of the bulk modulus is called compressibility and is denoted by K. It is defined as the fractional change in volume per unit increase in pressure. Okay, this is new from the other compared to the other modulus. Yeah, they are saying that when we take a reciprocal of the bulk modulus, it is it is called as the compressibility and is denoted by K. K is the reciprocal of the bulk modulus and is denoted by it's basically 1 by B denoted by K compressibility, and 1 by V which we already know is the uh, uh, B which we already know is the hydraulic strain by I mean hydraulic stress by hydraulic strain, which if we get the formula we will get it as minus 1 by delta P times delta V by V. It it is defined, compressibility is defined as the fractional change in volume per unit increase in pressure. It's better to derive it. Let's try. Hydraulic stress bulk modulus, which is equals to hydraulic stress by hydraulic strain. Hydraulic stress is represented by minus P, which is equals to minus P by delta V by V, and 1 by V, which is compressibility, K compressibility, which is represented by 1 by minus P, or which this we can represent it as minus PV by delta V. So it is minus PV by delta V. We can write it as K, which is equals to minus 1 by P into delta V by V. This is compressibility. The fractional change in volume per unit increase in pressure is called as compressibility. Clearly we can see in the formula the fractional change in volume per unit increase in pressure is called as compressibility. K, which is equals to 1 by B minus 1 by delta P times delta V by V. It can be seen from data given in the table 8.3 that bulk moleculi for solids are much larger than liquids, which are again much larger than the bulk modulus of gases. Solids have a much larger bulk modulus, meaning higher, like for they require higher stress for minimal increase in strain. I mean minimal decrease in volume with with copper. No, it is nickel having the highest bulk modulus, and followed by steel with being 160. There is a massive difference, followed by copper. These are solids. These are liquids. Water has a very less bulk modulus, 2.2, with ethanol being the least shown here, mercury being the highest. Gases, air at STP, standard temperature and pressure, it has 1 into 10 power minus 4, which is very small compared to liquids. Stress, strain, and various elastic modulus. Types of stress: stress tensile or compressive, Stress, two equal and opposite forces perpendicular to the opposite faces. Elongation, strain is elongation or compression parallel to the forces direction delta L by L. Longitudinal strain. Shape, there is a change in shape, yes. There is no change in volume, yes, that is also true. As length increases, radius decreases, so obviously there should be no change in volume. Elastic modulus, y equals FL by A delta L. Name of the modulus is called as Young's modulus. State of matter is solid. Shearing, shearing type of stress is shearing stress, which is sigma s, which is equals to F by A. Two equal and opposite forces parallel to opposite surface forces in each case such that the total force and total torque on the body vanishes. Strain, pure shear, that is theta or delta x by L. Change in shape, there is, yes, there is a change in shape. Volume, there is no change in volume. As the change in shape increases, the volume will be same. Elastic modulus, G equals F by A theta. Name of the modulus is shear modulus or modulus of rigidity. State of matter, it is solid. It is experienced by solids. Now hydraulic, that is type of stress, hydraulic stress. Forces perpendicular everywhere to the surface. Force per unit area. Pressure, same everywhere. Strain, volume change, compression or elongation, delta V by V. There is no change in shape as the force is normal and same at all points of the body. As such, there is no change in shape, but the volume will decrease as the body will become more denser. Elastic modulus, B, which is equals to minus P by delta V by V. It's called as bulk modulus. State of matter, it can be experienced by solid, liquid and gases. Solids are the least compressible, whereas gases are the most compressible. Gases are about a million times more compressible than solids. Gases have large compressibilities, which vary with pressure and temperature. The incompressibility of solids is primarily due to the tight coupling between the neighboring atoms. The molecules in the liquid are also bound with their neighbors, but not as strong as in solids. Molecules in gases are poorly coupled to their neighbors, very poor intermolecular bonding. The table above shows various types of stresses, strain, elastic moduli, and applicable state of matter at a glance. Example, the average depth of the Indian Ocean is about 3000 meters. Calculate the fractional compression delta V by V of water at the bottom of the ocean, given that the modulus of water is 2.2 into 10 power 9 Newton per 10 power 9 Newton per meter square. Okay, the pressure exerted by a 3000 meter 3 kilometer column of water on the bottom layer, which the formula pressure, which is equals to H rho G, H rho G, which is equal to 3000 into 1000, that is basically the density of water, into 10 meter per second square, which is equals to 3 into 10 power 7 kg meter per second square per meter second square. That is pressure. Three into 10 power 7 Newton per meter square. Fractional compression, that is delta V by V, which is equals to delta V by V, which is equals to stress by bulk modulus. We already know stress, that is pressure basically, force per area. We already know bulk modulus, it is given. The only extra formula we used here is the P equals H rho G or rho Hg formula, where all the values were given. Okay, then let's go to the, basically we will get the compression should be 1.36 into 10 power minus 2 or 1.36 percentage. That is the compression of water at the bottom levels of the Indian Ocean, which should be higher for oceans of higher depth or higher depths of the Indian Ocean itself, that is as the seabed is not constant. Okay, let's go to the next subtopic. That's Poisson's ratio. Poisson's ratio. The strain perpendicular to the applied force is called as a lateral strain. Okay, let's see that again. The strain perpendicular to the applied force is called as lateral strain. If there is an applied force and the strain is perpendicular in direction to the applied force, it is called as lateral strain. Simon Poisson pointed out that within the elastic limit, the lateral strain is directly proportional to the longitudinal strain. The ratio of the lateral strain to the longitudinal strain in a stretched wire is called as Poisson's ratio. Okay, basically, what lateral strain is, if there is the strain, the change in length per unit length, that is perpendicular to the applied force, is which may be due to decrease in radius. Let's clear it out. Lateral strain, which is proportional to longitudinal strain, because as the body stretches longitudinally, there is reduction in the radius of this object. Example, a cylindrical object. The fractional change in dimension perpendicular to applied stress. When you stretch a body, interatomic forces try to maintain volume for most materials approximately. So as the body becomes longer, its cross-sectional area tends to shrink. This gives a negative lateral strain proportional to the positive longitudinal strain. Proportionality constant, that is a Poisson's ratio, which is lateral strain by longitudinal strain. This negative sign ensures positivity of the mu Okay, then I'll continue it later from Poisson's ratio. Poisson's ratio